Hey grade 12 and welcome to this video. In this video, we're going to be working on the Mathematics Paper 2 NSC November 2021, but specifically the Euclidean Geometry section. Okay, so we have question 9, and question 9 says, in the diagram, PQRS is a cyclic quadrilateral. Then they tell us that PS is produced to W, so this is extending to W, and we have TR and TS are tangents to the circle at R and S respectively. Those are important. So these are tangents. Okay. Now, what else do they tell us? They tell us that angle T is equal to 78 degrees and angle Q is equal to 93 degrees. Okay, so they're giving us angles. When they give you angles, it actually feels much easier because at least you can see the numbers that these angles are equal to. So now we have 9.1 saying give a reason why ST is equal to TR. Okay, so let's look at those lines. Why would ST be equal to TR? Well, do you remember that in the beginning, in the scenario, they told you that ST and TR, right, that those are tangents. You see, TR and ST are tangents to the circle at R and S respectively. So if you have a tangent to a circle, and they're drawn from the same point, then they're going to be equal. So that is the reason that they are equal, because we have tangents that are being drawn from the same point to the circle. So they will be equal in length from that point till their point of contact with the circle. And so there we go, 9.1, it is because tangents drawn from the same point to a circle are equal. Okay, so let's just keep in mind that those two are equal. Then the next question says 9.2, calculate given reasons the size of, first of all, angle S2. Okay, so how can we find angle S2? Well, it is part of this triangle SRT, where we know that these two sides are equal. If you have two sides in a triangle equal, then this is an isosceles triangle, and so therefore two angles will be equal. So just remember, the angles that will be equal are the angles that lie opposite these equal sides. So you see we have this side being equal to this. So the angle that lies opposite it is R2. So angle R2 would be equal to, then you look at this equal side, the angle would lie opposite it. So angle R2 is equal to angle S2. So we can start by stating that because we know these two are already equal. So in 9.2.1, we can first of all tell them that angle S2 is equal to angle R2. And now what's our reason for this? Well, it's not really isosceles triangle, but what we say is angles opposite equal sides are equal. So because these angles, they lie right opposite two sides that are equal. So it means that those angles are equal. Okay, so now that we have that down, we can solve for angle S2 because they want us to solve for angle S2. Now, notice that in this triangle, we have three angles as usual. So if we take this angle and we add it to this angle and we add it to that angle, it should sum up to 180 degrees. Okay. Now remember, I've already said that angle S2 is equal to angle R2, and we know we need to find angle S2. So when I'm adding these angles up, look at how I'm going to add it. I'm saying angle S2 plus 78 degrees, of course, and plus angle R2. But instead of calling angle R2, I'm just going to call it angle S2 since I already said that they were equal. So this is plus angle R2, but I'm just going to call it S2 because they are equal and I want to make S2 the subject so we can solve for angle S2. So plus angle S2 is equal to 180 degrees. And our reason, of course, is because of the sum of angles in a triangle. Okay, now we can just solve for angle S2. Notice that you have an angle S2 plus an angle S2, which will give you 2 angle S2. Plus 78 degrees is equal to 180 degrees. And so 2 angle S2 is equal to 180 minus 78. So that's 2 more degrees to 80. So it's 102 degrees that is going to give you. And then you just divide both sides by 2. And so it means that angle S2 is equal to, and divide by 2, we have 1 and 50, so 51 degrees is our answer. So there we go. Angle S2 is equal to 51 degrees. Now, when you have something down, it's best to actually write it in the diagram because it will probably help you. So we know what angle S2 is. That's 51 degrees. We also know that this is the size of angle R2. It's also 51 degrees. Okay, so moving on to the next question. 9.2.2 says we need to determine the size of angle S3. So angle S3, this angle over here. Okay, so looking at this, you're going to have to just look at where exactly S3 is. Unfortunately, it's not a tangent, this line over here. But do you notice that this line, okay, this is a cyclic chord, and this side of the cyclic chord is extending. It means we have an exterior angle in this cyclic chord. So this is the exterior angle. It starts from here, and it's going to be going all the way to the actual cyclic chord. So this entire thing is your exterior angle. The exterior angle of a cyclic chord is always equal to the opposite interior angle. Okay, so now we know that angle S3 with angle S2, when we add them together, they form the exterior angle, and they should be equal to this angle Q. So I'm going to actually state that down first. So I'm saying that angle S3 plus angle S2, because that makes up the full exterior angle, it should be equal to angle Q. It should be equal to angle Q. And our reason for that is exterior angle of a cyclic chord. Okay, so now we're going to go ahead and say angle S3, because it's what we're looking for, angle S3 plus angle S2, which we have as 51 degrees. Plus 51 degrees is equal to angle Q, which is 93 degrees. It's 93 degrees. Then angle S3 is equal to, we're going to take 93 degrees and then take 51 degrees over. So that's 93 minus 51, which is going to give us 42 degrees. And there we go. Angle S3 is equal to 42 degrees. Okay, so that is it for this little part in question 9. Then we move on to the next questions. Okay, and then now we're on question 10, and question 10 says, in the diagram, BE and CD are diameters. Okay, so we have BE and CD. Then they are diameters of a circle having M as the center. Chord AE is drawn to cut CD, so AE is drawn to cut CD at F. And we can see now that AE is perpendicular to CD. Okay, so they're saying let angle C be equal to X. Okay, so we already have this, and the first question is 10.1. Give a reason why AF is equal to FE. So why is AF equal to FE? Well, first of all, see that you have a right angle here. Because you have a right angle here, and remember they told us that angle, that M, right, that point is the center of the circle. So we see that there is a line drawn from the center of the circle, and it happens to be perpendicular to this chord AE. So the line drawn from the center of the circle, perpendicular to the chord, what does it do to that chord? That line bisects the chord. This is the first theorem that you usually learn when working with circle theorems. So that would be the reason that AE would be equal to FE, because the line drawn from the center of the circle, perpendicular to the chord, bisects the chord. Okay, so I'm just going to put a marker to know that they are equal. So these two lines are equal. Okay, so moving on to the next question. 10.2 says, determine given reasons the size of angle M1 in terms of X. So when we find angle M1, it should have X in it. It should have something to do with X. So let's look at angle M1. You see, how you're going to find these answers is you look at the angle M1 first of all, and then ask yourself, where is this angle? So that you can know which type of theorems you're going to apply to it. One thing I noticed about angle M1 is that it's at the center of the circle. So we can think about angles at the center of the circle. What kind of theorems do we have there? Well, we know this theorem about the angle at the center is twice the size of the angle at the circumference as long as they are supported by the same chord or arc. So looking at angle M1, what is angle M1 being supported by? Well, if you drew this just to form the angle M1, like that and like that, you see that angle M1 is being supported by this arc CE. So what else is being supported by that arc CE? So looking at that arc CE, we can also see here, look at this, there's another angle being extended. So here, like that and like that. So there, angle A1 is also supported by arc CE, and angle A1 is at the circumference. So it means that M1 is going to be twice the size of A1. Okay, that does not really lead us yet to X. But looking at it like this, do you see that angle A1? Look at where it is in this diagram. It is part of a triangle, ACF. And in this triangle, we have something that is equal to X, and we have a 90-degree angle, meaning we can find angle A1. And that's where we're going to start. You see, we already know there's going to be a relationship between M1 and A1. So we just have to find A1 first, then we'll sort that one out. Okay, so focusing on angle A1. So angle A1, I'm just going to find that. And I'm saying that angle A1, of course, plus angle C, which is X. So plus X, plus that angle over there, which is 90 degrees. If you add all of them up, they're going to give you 180 degrees. So it's equal to 180 degrees. And the reason is, of course, the sum of angles in a triangle. And then we're just going to make angle A1 the subject because we're trying to solve for angle A1. And this is equal to, we have 180 degrees, and we'll take 90 over minus 90, take X over minus X. And so A1 is equal to 180 minus 90 is 90, and then we have minus X. So this is angle A1. Now remember, angle A1 is related to angle M1. We remember that the angle at the center must be twice the size of the angle at the circumference. Okay, so we're saying that angle M1 is going to be twice the size of angle A1 because they've been supported by the same arc CE. Okay, so now we're just going to solve for angle M1. So it means that angle M1 is equal to, okay, I have to put the reason that's angle at the center equals to twice the size of angle at the circumference. And now we're finally solving for angle M1. So this is 2 multiplied by whatever the value of angle A1 is, which you can see is 90 minus X. So because it's 2 terms and we need to multiply to 2, you're going to have to put brackets. So this is 90 degrees minus X. So therefore, angle M1 is just equal to 180 degrees minus 2x. And that is your answer there. Okay, and then the next question is 10.3. And it says, prove given reasons that AD is a tangent to the circle passing through A, C, and F. So we're proving that AD is going to be a tangent to a circle that passes through A, C, F. Okay, so this means that we have a circle here at ACF. You have to actually draw the circle. And we have to prove that AD is the tangent of the circle. So let me draw the circle first. So we have some sort of a circle, and in this circle, we have to prove that this is the tangent, okay, of the circle. That is a tangent to the circle. This type of question has shown up a number of times. You will see them a lot in the November papers as well. So this is how you're going to be able to prove that this is a tangent to this circle. So there's a theorem that speaks about a tangent to a circle. Do you remember the theorem that says that the angle between the tangent and the chord is always going to be equal to the angle that is supported by that same chord? So the angle between the tangent and the chord, this is not a tangent yet. Okay, that's true. But if we can show them that the angle between the thing that's supposed to be a tangent, which is A2, this is angle between the tangent and the chord. If we can show them that this angle is equal to the angle opposite this chord, which is, of course, angle C, which is X. If we can show them that these two angles are equal, then it would make AD a tangent. Okay, so that's all we're trying to do. We're trying to prove that angle C is equal to angle A2. So that's what we're going to keep in mind. Prove that angle C equals angle A2. Okay, so to do this, to prove that angle C is equal to angle A2, you can start from either one of them. Right now, this is not a tangent yet. We're just trying to prove that it is one. Okay, so to prove this, first of all, I think we need to include those that we found already. Like angle A1 was 90 minus X. So I'm actually going to leave that there in case it is useful. So this is 90 minus X. And then angle M1, remember, was 180 minus 2X. So I'm also just going to leave that there, 180 minus 2X. Okay, so we're just trying to find out how will this eventually be equal to X. Okay, so since we have these angles down, what we can do is, remember, we're just trying to prove that these two are equal. Since this one is already equal to x, we can try and find out how this one is equal to x, or really just trying to find the size of this angle over here, angle A2. Okay, so looking at angle A2, it is at the circumference, meaning you could have also thought about rules having angles at the circumference. You know that if you have two angles that lie at the circumference and they're supported by the same chord or arc, then they will be equal. But in this case, you see that this angle A2 is supported by this arc ED. And then I can't really see any other angle at the circumference that is also supported by ED. I do see an angle at the center, and we could have actually found it like this. We can find this angle at the center, and then we'll be able to find A2. But just because they didn't name this, it's not that you can't use it. You can. But I feel as if there's an easier way, just given the fact that they didn't decide to name this like M4. Okay, because this is M1, 2, 3. They should have named it M4 if they really wanted us to really touch that. So I'm not going to go with that. Let's look at other options. So it's at the circumference. Okay. Do you realize that this CD is a diameter? So if you have a diameter, remember that the angle supported by a diameter is always going to be equal to 90 degrees, meaning angle A1 plus angle A2 together give you a 90-degree angle because they are supported by this diameter CD. So I'm going to add angle A1 with angle A2, okay, and say it's equal to 90 degrees. Okay, and this is because of angle in a semicircle. So let's see, A1 was this. That is 90 degrees minus x plus A2 is equal to 90 degrees. Okay, so plus angle A2 is equal to 90 degrees. And now we can go ahead and just solve for angle A2. So I see a 90 and a 90 and they're both positive. You can cancel them out. Or if you like, you can take that over and you'll see that it will become a negative 90, which will cancel with a positive 90. But I'm just going to cancel them on both sides because I see that they do cancel. Then we'll be left with a negative x here. We can take that over to make it positive. And here on the left-hand side, we'll be left with A2 is equal to, we're taking that over, positive x. So there, angle A2 is equal to positive x. And because we already knew that angle C originally was already equal to x, that would mean that both of them are equal. So that means, therefore, angle C is equal to angle A2. There we go. Okay, so that's just a conclusion for here. Since now angle C and angle A2 are actually equal, so I can just call this angle A2x. Since they are now equal, that would prove that AD is really a tangent to the circle that passes through ACF because of the tan chord theorem worked perfectly there. Okay, so there's our conclusion, and it's really because of the tan chord theorem, which we never really write like this in matric, especially in the final exams. You're going to have to write the full theorem. Okay, so there is our conclusion, and the reason for that is it's not really the tan chord theorem itself, it's the converse of it because we used it backwards. The tan chord theorem is usually given that this is a circle, this is a tangent. Then you'll be able to conclude that this angle will be equal to that angle. But in this one, we started with a conclusion. We started, first of all, with proving that this angle is equal to that angle, and so therefore, AD is a tangent. So it's really the converse of the tan chord theorem. Okay, so that is the end of that question. So moving on to the next question. So 10.4 says, given that CF is equal to 6 units and AB is equal to 24 units, calculate given reasons the length of AE. Okay, so I just pinned that on top just so that I can see what exactly is equal to the specific amount of units. So we have CF, first of all. CF is equal to 6 units. So let's just mark that down. CF, this is 6 units. And then AB is 24 units. So AB is 24 units. Okay, and we have to now calculate the length of AE. Okay. Okay, so looking at this, we have AB. And they also gave us CF. Now, in a way, it's like, why are they giving us CF? What is the whole point of that? Because the AB part, if you look at this shape that we have here, see this big triangle that we have, right? we could possibly use proportionality theorem. Okay, so we have this big triangle, and now they want us to find out what exactly the length of AE is. Notice that AF is equal to FE. Okay, those two are equal. So this is actually more of the midpoint theorem now. But these two lines are not parallel. Okay, so keep that in mind. The two lines are not parallel, so we cannot just start using the midpoint theorem. If we want to use the midpoint theorem on this, we're going to have to show them that these two lines are parallel. Okay, but let's just focus on what we want to find. Since we want AE, is it necessary to use the midpoint theorem? Well, yes, it is actually necessary to use the midpoint theorem, because look at this. We want the length of AE, and you know that AF plus FE make up AE and they're equal to each other. So you just have to find one of it. If you can even find FE, you'd be able to find the full length of AE. So the reason why this would be important to find the midpoint theorem is because of the fact that if we eventually find out that these two lines are parallel, it would mean that in the midpoint theorem, remember, your midpoint theorem, you are given two lines that are parallel and these two are equal. But also just do remember, let's just say I call it ABC and this is DE. Remember that BC, that longer one, is always going to be twice the size of the shorter one, DE. Now, why am I saying that? Because here we have AB. If AB is twice the size of FM, then that means we'll be able to find the size of FM. This is important because this can help us if we use this as a right angle triangle, because this is a right angle triangle. We have 90 degrees there, so this is definitely 90 degrees. We would have this side, would be looking for this side, and if we get the radius, we'd eventually be able to find that using Pythagoras. So the right angle triangle, if we finally find what ME is, that radius, because it's going from the center to the circumference, if we find out what that is, and we of course find out what FM is, then we'll be able to find FE. So if we find FE, it will be easy to find AE because it's just going to be double the size of that. Okay, so to use the midpoint theorem, you need to have that two sides are equal and you have a pair of parallel sides like that, okay? One side is drawn parallel to the other side of the triangle. But as you can see, they did not tell us that anything was parallel yet. They didn't tell us that these two lines were parallel. Okay, so looking at this triangle, now I'm actually starting to see that, look at what we have here. You see EM and MB, they're both radiuses of the circle. They're radii. So because of that, it would mean that these two lines are equal to each other. So we can note that down first of all. We can tell them that ME is equal to MB, okay? So let's go ahead and put that down first. So ME is equal to MB because these are equal radii. Okay, now that we have that, let's see. Since we have that, look at our diagram now. Remember that we already know that these two lines are equal. AF and FE are equal. And now we also know that ME is equal to MB. So this is actually what we have here. We don't have the lines are parallel, no, but we do have this. We have this being equal to this and this being equal to this. This is the converse of the midpoint theorem. If you are ever given that AD is equal to DB and AE is equal to EC, it would conclude that DE is parallel to BC and of course that BC is twice the size of DE. This is the converse of the midpoint theorem. So remember, with these theorems, you always have to look carefully at what you have been given, and based on what you have been given, you have to be able to see what you have to conclude. So because those two are equal now, I'm going to conclude that these two lines will be parallel to each other, that FM is actually going to be parallel to AB. Okay, but first of all, I'm just also including that these two are also equal because I'm just trying to show them that that is equal to that and this is equal to this as well. Okay, those lines are equal. So when I say AF is equal to AE, I'm just going to say proven because this has already been proven previously. Really just at the beginning, we already proved that. So now this would mean that those two lines are parallel. Now we finally know that FM is parallel to AB. So Therefore, FM is parallel to AB, and our reason is the converse of the midpoint theorem. Okay, so now that they are parallel, let's see how we can use them. Since they are parallel, remember we can now find FM. The whole point is to find FM because we're going to use that as a right angle triangle so that we can find the other stuff as well. Okay, so this means that AB is going to be twice the size of FM, just like we have here. See, the longer one is always twice the size of that shorter one. So I'm going to state that AB is 2 times the size of FM. Okay, and of course, this is for the same reason. These are the 2 things that you conclude using the converse of the midpoint theorem. When you're given these 2 situations, that those 2 lines are equal on those 2 sides, then we conclude this. Okay, so now I can finally find the length of FM. I know the length of AB already. That was 24 units. So I'm saying 24 is equal to 2 multiplied by FM. So solve for FM, we'll divide both sides by 2. And so it means that FM is equal to 12 units. Okay, so we got FM. So we can fill that in and let's see. So this is now 12 units. Okay, now that we have this, remember the whole point is to find AE, but we're just going to find FE first. So in order to find FE, we have FM in this right angle triangle. We would also need ME. But ME is a radius, which is great because it is a line drawn from the center of the circle to the circumference. So since this is from the center to the circumference, this is also going to be from the center to the circumference, from M all the way to C. That is also from the center to the circumference. And that is the reason they were telling us what CF was, okay, or FC. That is 6 units. So now we know that the radius from M to C, right, that is actually going to be 12 units plus 6 units to create that full radius. And because all the radiuses or radii are equal, it would mean that ME is also going to be equal to that. So that's what I'm going to say. I'm saying ME is going to be equal to MF plus FC. And the reason for that is equal radii or just radii. That will be fine. And so ME is equal to the 12 plus 6. As you can see here, that's 12 units plus 6 units. And then that gives you 18 units. So therefore, ME is equal to 18 units. Okay, so we have 2 things now. And now that we have these 2 things, we can basically find the length of FE because we know what ME is now. Since it is their equal radii, then it means that this one is also 18 units, right? That's what we just found, 18. So we know this is 12, this is 18. We can use Pythagoras to find FE. So let's go ahead and find FE now. So we'll find that by saying that FE squared, right, because we're looking for that, is equal to the hypotenuse squared, so it's ME squared, minus the shorter side square, which is MF or FM squared. Okay, so we're going to do that. And the reason for this, of course, will be Pythagoras. So we're using the theorem of Pythagoras. And now we're just going to fill in. So FE squared is equal to ME. We know that is 18 units. So 18 squared minus MF, which we already know, MF or FM is 12 units. So minus 12 all squared. So FE squared is finally equal to, and we just put this on the calculator. And you see we get 180. And then if you square root both sides just to find FE, so FE is equal to what is the square root of 180 degrees. It is, I'm just going to put it in third form so long. So 6 square root 5. Okay, so now we know what FE is. The whole goal is to find the length of AE. But remember that AF is equal to FE. So since this is 6 square root 5, then AE is going to be 6 square root 5 plus 6 square root 5. Or really just times that by 2 because it's both of those lengths together. Okay, so it means that AE is finally equal to 2 multiplied by 6 square root 5, which is going to just give you 12 square root 5. And then we can also just see what this is going to be on the calculator as 12 square root 5 in decimal form. So this is going to be rounding off to 2 decimals, just like they always mention in the instructions. So this is going to be AE is equal to 26.83 units. And there we go. That's the length of AE. Okay, moving on to the next question. Okay, so the next question, we're going to have a proof. As you can see, they've given us this. They want us to prove the tan chord theorem. And now we're on question 11 of this paper. And in question 11.1 says, in the diagram, chords DE, EF, and DF are drawn in the circle with center O. KFC is a tangent to the circle at F. And we have to prove the theorem which states that angle DFK, so this angle DFK, is equal to angle E. So this is the tan chord theorem. We have to prove the theorem that states that the angle between the tangent and a chord is equal to the angle supported by the same chord. Okay, so I do have a video on the tan chord theorem along with the other circle theorems and also some triangle theorems. Okay, the proofs of them are on my channel. You can go ahead and watch those videos. But for the sake of this video, I am still going to do this proof. Okay, so the tan chord theorem is one of the simplest theorems to prove. So if you do see it, it's a good thing. It won't be that difficult. First of all, when we want to prove the tan chord theorem, we're going to construct a diameter. So we're going to construct a diameter and we're going to let that diameter intersect, or rather, let's just say bisect this angle over here. So this is what we're going to do. We're constructing a diameter that will go like this and it passes the center of the circle, of course. So this will be a dotted line normally. Okay, like that, because it is a construction. And then after constructing the diameter, you see from this endpoint of the diameter, you're going to construct a line that is going to meet this angle over here. And the whole point of this is so that we can have a diameter and an angle supported by a diameter, which we know angles supported by diameters are always going to be 90 degrees. And the whole point of having this here is so that we can have OF as a radius, which is clearly intersecting this tangent. And we know that the radius is always perpendicular to the tangent at the point of contact. Okay, so since I have created that, I'm going to actually just call it something. I'm going to call it P. And then you have to write down all constructions that you have made. So here I have stated that I have constructed the diameter POF, this diameter, and the chord PE. Okay, so now that that is done, we can start proving this theorem. So the first thing we're going to do is, let's go ahead and name these angles. So you see this little angle over here, we're going to call that E1, and we're going to call this E2. You can also let them know of all the angles that you've been naming. This one is F1 and this one is F2. So I'm also just going to let them know of the angles just in case as well. Okay, so I've also named the angles as well. I'm telling them that I'm going to let the angle PED be E1, the angle DEF be angle E2, and then the angle PFD be angle F1, and the angle DFK is F2, just in case. Okay, so now we can go ahead and start proving this theorem. So as you can see, what they want us to prove is that the angle DFK is equal to angle E. So this angle over here should be equal to angle E, angle E2 basically. Okay, so now that we have put this down, it's going to be very easy from here. All we're going to do first of all is, we'll look at the fact that OF is a radius, okay, from the center to the circumference. And you know that the radius and a tangent, they're always perpendicular at their point of contact. So we're going to let them know that. So first of all, we're going to say that OF is going to be perpendicular to KFC. And that is because radius is always going to be perpendicular to the tangent. Okay. And then after we have let them know that, that means that the angle F1 plus angle F2 is going to be equal to 90 degrees since this is perpendicular. Okay. And now that we have that down, we're also going to look at this. Remember that this is a diameter, POF. And so the angle subtended by a diameter is always going to be 90 degrees. So we're also going to let them know that angle E1 plus angle E2 is going to be equal to 90 degrees. So angle E1 plus angle E2 is equal to 90 degrees. And our reason for that, you can say angle subtended by a diameter, or you can say angle in a semicircle, which I'm going to use. Okay, so look at what we have right now. Now, the thing about this is just because angle F1 plus angle F2 gives you 90 degrees and angle E1 plus angle E2 gives you 90 degrees, that does not mean that angle F1 and angle E1 are now equal and F2 and E2 are now equal. That doesn't prove that yet. They just add up to 90 degrees on their own. So we need to find two other angles that are first equal in these two cases first. So what we're going to do is we will use the bow tie theorem, okay? Angles in the same segment. So if you look at this diagram, do you notice that the arc PD is supporting this angle at the circumference? Let me actually put this in a highlighter so that I can erase it. It's supporting the angle at the circumference, angle F1. And also notice that it's also supporting the angle at the circumference, angle E1. So that would make angle E1 equal to angle F1. So we're going to state that down. So this means that angle E1 is equal to angle F1. And the reason for that is angles in the same segment. And now that these two are equal, you see, we're saying that angle E1 is equal to angle F1. But we know that when you take angle F1 and you add it to F2, it gives you 90. And if you take E1 and you add it to E2, it also gives you 90. Because these two are equal, by default, that makes these two equal as well. So now finally, I can conclude that this means angle F2 is actually equal to angle E2. And if we go back to the diagram, you notice that angle F2 is that angle they were referring to, DFK. So angle F2 is DFK. So I can conclude that this means that angle DFK is actually going to be equal to, the cap should be on that. So it's equal to angle E2, which is of course, in their sense, that was angle E that they were speaking about, which is equal to angle E. Even if you left it like that, it will be fine. So there we go. That's how we prove that theorem. And if you wanted to understand this better, you can go ahead and look at the proof on this theorem on my channel, because I give a slightly deeper explanation into this. Okay, so that was question 11.1, and moving on to the next question. 11.2 says, in the diagram, PK is a tangent to the circle at K. So we have PK being a tangent to the circle at this point K, and chord LS is produced to P. So here's LS being produced all the way to P. And then we have N and M are points on KP, NMM, and they tell us that and SP respectively, such that MN is parallel to SK. So that is a very important piece of information. We have parallel lines there. Then chords KS and LN intersect at T. So there they just intersect at T. The first question is 11.2.1a. We have the proof given reasons that angle K4 is equal to NLM. So let's just mark those angles. So they want us to prove that angle K4, this angle over here, which as you can see, you have a tangent and a chord, okay, that it's equal to the angle NML. So NML, this whole angle. Okay, so how can we prove that? Okay, so if we start at angle K4, because this is a tangent, we have this tangent and we have this chord KL. So we know that the angle between the tangent and the chord should be equal to the angle supported by the same chord. Okay, and it must be at the circumference, of course. So we have this chord KL. Which angle at the circumference is being supported by KL? So that would be this angle, angle S1. So we know that these two angles are equal. Let's take that down first. So we're saying that first of all, angle K4, and let me put this in black, angle K4 is equal to angle S1, and it's because of the tan chord theorem. Okay, so because of the tan chord theorem, okay, so basically what we've just done is we've moved from angle K4 to angle S1. So from angle S1, how can we find a way that this ends up being equal to NML? Okay, but see, we have parallel lines. So because we have parallel lines, we have, if we draw an upside down F like this, you see that we have corresponding angles. So angle S1 is going to be equal to angle NML because of corresponding angles. So that's how we actually get that one. So there we go. Angle S1 is equal to angle NML because of corresponding angles. Okay, and I just made sure to say exactly which lines were parallel. And so because of this, as you can see, K4 is equal to S1 and S1 is equal to NML. So this concludes that angle K4 is actually equal to angle NML because they're both equal to angle S1. Okay, so that is that, and it is for 4 marks. As we can see, there are 2 steps. So you get a mark for your statement, your reason, statement, and reason. So that is 4 marks. Okay, moving on to the second question. So the next question here is prove given reasons that KLMN is a cyclic quadrilateral. So let's just mark that out. K, L, M, and N. Okay, so we have to prove that it's a cyclic quad. Okay, so here is KLMN. I'm not really drawing a circle around it, but I did mark it out. So we have to prove that this is a cyclic quadrilateral. So remember, there are 3 theorems that you can use to prove that something is a cyclic quadrilateral. The first one is this theorem that tells us that the angles at the circumference supported by the same chord or arc are equal. If you have that scenario, if you have that case where you find angles at the circumference supported by the same chord or arc and they're equal, then this shape is a cyclic quad. The second scenario is if you have a cyclic quad and you notice that the opposite angles of the cyclic quadrilateral are supplementary, meaning they add up to 180 degrees, then you know that this is a cyclic quadrilateral. And then the third case is if you have a cyclic quad, so just a quad inside, and you notice that the exterior angle of the cyclic quad is equal to the opposite interior angle, then this will be a cyclic quadrilateral. So let's look at the shape and see, how can this be a cyclic quadrilateral? So looking at the cyclic quadrilateral, you notice that this is the exterior angle of the cyclic quad, that angle K4. And you notice that angle K4 is already equal to this angle here, NML. So this proves that this shape is actually a cyclic quadrilateral. Okay, so we can go ahead and put that down. It means that angle, we know that angle K4 is equal to the angle MNL. So that means actually NML, sorry. So NML. So that concludes that this is a cyclic quad. So you're just going to name the quad and then say that it is a cyclic quad and of course give a reason. So KLMN is a cyclic quadrilateral because the exterior angle of the quad was equal to the opposite interior angle. Okay, so that is that question. Moving on to the next question. Okay, so the next question, 11.2.2, says, prove given reasons that triangle LKN is similar to triangle KSM. So first of all, let's highlight those triangles. Okay, so I don't really need these. As long as we know now that this shape is a cyclic quad, so we can use cyclic quad properties on it. And then we can highlight the circle KSM. Okay, so to find out how we can prove that they are similar, remember, when triangles are similar, it really just means that all their angles are equal. And so if all their angles are equal, you're going to find that the sides will be in proportion. So there's really just 2 ways to prove that triangles are similar. You can either prove that all the angles are equal or all the sides are just in proportion. Then you know that these 2 triangles are similar. But in this situation, we're going to try and prove that all the angles are equal because as you can see, they have not given us the lengths of any of the sides of these triangles. Okay, so we're working with angles. Now, the way in which they name the angles is very important, and this should guide you. Instead of just looking for how maybe which angle is equal to what angle, follow the way they have named the angles for you. Remember, the first triangle is called LKN. I'll just use it from here. So if it's called LKN, it means that L is the first letter that they mentioned. It's going to correspond with the K in the next triangle. So let's look at that. See, LKN. L refers to this angle, L1. That is the angle that is probably equal to the angle K, okay, in the other triangle. So that's KSM. So that is the angle K2. Now we're going to look at both of them and ask ourselves, how can these two be equal? And spend some time on this. If you see that you can't really find a way that these two can be equal, that's okay. Go to the next letter. So I'm just going to look at it now and say, how can angle L1 be equal to angle K2? Okay, so the first thing I see is angle K2 is in a very nice place because it is between these two parallel lines. We could draw a Z for alternate angles, and you would notice that angle K2 is going to be equal to angle M2. Okay, then do you notice that angle M2, because this shape KLMN is now a cyclic quadrilateral, we can use cyclic quad properties on it. Do you notice that angle M2 is being supported by Kn, and angle L1 is also being supported by Kn, and they're of course at the circumference of their circles, okay, because there's supposed to be a circle here. I didn't really draw it because I couldn't really draw a proper circle right here, okay, but remember that that is a cyclic quad. So we just found one way now that L1 can be equal to angle K2. So K2 was equal to M2 because of alternate angles, and then angle M2 is equal to angle L1 because of angles in the same segment, and they're being supported by the chord Kn, okay, because that is a cyclic quadrilateral that we have there. Okay, so first of all, let's introduce the circles. When you want to prove that triangles are similar, you first need to introduce them by saying in triangle, and then we're going to name them. So in triangle LKN and triangle KSM, what do we have? Remember, we're working with this K2 first of all. So angle K2 first of all is equal to angle M2 because of alternate angles. Angle K2 equals angle M2, and that is because of alternate angles. And you can say on parallel lines, so you can tell them which lines are parallel. That was the line MN is parallel to ST, right? Those two lines because of, okay, we can call it KS, it's fine. KS and MN are parallel. And then angle M2 is equal to angle L1 because this is a cyclic quadrilateral, and so these two are at the circumference of that cyclic quadrilateral. They're angles in the same segment. So angle M2 is equal to angle L1. Okay, so of course that would conclude that angle K2 in that triangle is equal to angle M2 in the other triangle. Okay, the next angle that is equal. So we're just going to keep following this. You see, we found one angle. The thing about similarity that is really nice is that you really just need to find two angles that are equal in two triangles, in the two triangles. If you find two angles that are equal, by default, the third angles in both triangles will be equal because, of course, of the sum of angles in a triangle. Okay, so I've worked with L and K. So now let's work with this K here and S here. Okay, so the K here is referring to the triangle is named LKN, so it's referring to this whole thing as K. That is K1 plus K2 plus K3. Okay, that angle is somehow equal to this angle S in the green triangle, so that is KSM. So KSM S, so this angle S2. So we're just going to look at that for a while and see how can those be equal. If you can't find it, it's fine. Move on to the next letter. Remember, feel free to pause the video to actually try this on your own. It is better to attempt trying this first before looking at the video, okay, of somebody explaining it. Okay, so looking at that, I see now that S2, right? You see here it is by the parallel lines. So we can have corresponding angles. If we draw an F over here, we have corresponding angles, and so S2 would be equal to angle M1. Okay, then from angle M1, if you're looking at the cyclic quadrilateral KLMN, notice that angle M1 is an exterior angle of that cyclic quad, so it's going to be equal to the opposite interior angle, which would be this entire angle here, that angle MKL, K1, K2, and K3. Okay, so that is how those two are equal. Okay, so let's put that down. First of all, we're saying that from angle S2 is equal to angle M1 because of corresponding angles. Okay, so first I've put that down. Angle S2 is equal to angle M1 because of corresponding angles. And I've also put the lines that are parallel. Now I just have to say angle M1 is equal to this opposite interior angle of the cyclic chord NKL. Okay, so of the cyclic chord KLMN, this is the opposite interior angle. So angle M1 is equal to MKL. Okay, so angle M1 is equal to angle NKL because of exterior angle of a cyclic chord. Okay, so now that we have that, and you can see S1 and NKL are both equal to angle M1, so that of course concludes that finally angle S2 is equal to angle NKL. Okay, so those are the two angles in these two triangles. That is that center angle K, and we have S over there. Okay, so because they're equal, I'm just also going to put some sort of line or marker so that I know they're equal. So I use two lines for this, one line for that one. So just use something like that, 3 lines. So I know that this is actually equal to this angle over here, which is of course equal to this angle over here. Okay, so it's getting really messy, but we must just keep focusing on what's going on. Okay, you see now 2 angles in the triangles are equal. That's all you need. The third angles in both triangles will be equal by default, okay? Because the triangles must still always add up to 180 degrees. So the third angle is now going to be equal in both triangles. So we're going to name them. See, the last letter we're looking at is N. So from this triangle, LKN. So that's angle N3. So now we know angle N3 should by default be equal to that last M here in KSM. So KSM, so that last angle, angle M3. These two will be equal by default because of the third angle in a triangle. Okay, so there we have 3 angles in the triangles equal, and we can finally conclude that triangle LKN is now similar to triangle KSM, and that's of course because of angle, angle, and angle. 3 angles were equal. Okay, so there we have proved that these 2 triangles are similar. So you see how you can prove that now. The naming of it really helps you a lot. It's going to guide you on which one should be equal. But you mustn't just say that they are equal. You need to find out why they are equal. It just gives you a guide on which ones will be equal. And just remember, if you're really struggling to find why those 2 angles in the 2 triangles are equal, just skip over to the next letter. Okay? Find out why those 2 are equal. You just need to find at least 2. By default, the last angle in both triangles will be equal by default. Okay, moving on to the next question. Then the next question, 11.2.3, says if LK is equal to 12 units and 3KN is equal to 4 SM, determine the length of KS. So first of all, I just want to point out, whenever they give you things like this, they're actually just trying to give you the proportions. See, you can rewrite it like this. So 3KN being equal to 4 SM. What you're going to have to do is put the numbers on one side and put the letters on one side. So we're going to have to divide both sides. We're going to have to decide where we want the numbers to be. Just to make it look okay, I'm going to put the numbers on this side. So I've decided I want only numbers here, meaning I want this 3 to go here. But remember, the 3 has been multiplied to the kn, so the only way to get rid of it is to divide both sides. So first of all, I'm saying to get the 3 there, I'm going to divide both sides by 3. And there, the 3's here would cancel, and now we have 4 over 3 here. Then next, because I don't want any numbers here, I just want letters here, I want only letters to be here, meaning this SM needs to come over here. So to get it to become this side, to come over to this side, I'm going to divide both sides by SM. So again, we're still dividing. I'm dividing both sides by SM. And now things will just cancel the way they're supposed to. So here, the 3 and the 3 is gone. We have KN over SM. And then here, SM and SM will cancel. We have 4 over 3. So this is actually what they're telling us. They're telling us that KN over SM is equal to 4 over 3. They're giving us the ratio. and they told us that LK is equal to 12 units, sorry. So 12 units. So let me put that down and we can look up in the diagram and see how we can find the length of KS. Okay, so I'm just trying to see what exactly are the lengths they've given us and from where. So first of all, they told us that KN over SM is 4/3. So remember, this is just the ratio, meaning it's describing how the lengths are shared. KN is getting 4 parts, SM is getting 3 parts. So this is what I'm going to write. For KN, I'm going to write 4K, just so I do not confuse this as the amount of units. This is not the length of KN, it's just the ratio. And then SM is 3. So SM is getting 3 parts, 3K. That's what I'm going to call it. Then they told us that LK is equal to 12 units. So LK, so we have L all the way to K is 12 units. So this is 12 units. And we need to find exactly what KS is going to be. Okay, so since we need to find KS is over here. Do you notice now, look at the sides that they're using. They're using the proportions of this triangle. These two triangles, LKN and KSM. They're using those. So what we're going to do is, we know that they're already similar. We're going to use the fact that they're similar to find what exactly KS is going to be. So this is how we can do that. We can do that using the conclusion. You see, the conclusion is very important, and that's why when they name it for you, which they usually will, it's a good thing to continue writing it like this because it is in proportion like this. So this is what we can say. This means that from this, we can conclude that LK over, so you see I'm taking LK. Now I have to correspond as well here. Since I took the first and the second letter, I must take the first and second letter here as well. So over KS would be equal to KN over SM. Okay? And lastly, LN over KM. That's how we're going to look at them. That's how the proportions will work. But you need to take the proportions of things that you need to focus on. Like, first of all, you see we got KN over SM. So you need to have KM over SN. And I can see that here. I will take that part. And then they told us the length of KL. So you need to take one of the proportions that has KL. And as you can see, they told us to look for the length of KS. So we're looking at a proportion that has LK and KS. And that will be this one over here. Okay, so that's what we're going to use. We're going to use these proportions. So I'll start off by saying that LK over KS should be equal to KN over SM. Okay, and the reason I can use that is because these triangles were similar triangles. Okay, so I'm using these proportions from the fact that the triangles were similar. Okay, now we can go ahead and say LK, what was that? That was 12 units. So I'm going to put that 12 units over KS, which is what I'm looking for, is equal to, and we have KN. KN is 4K, of course, 4 parts, but I'll just say 4 over SM, which is 3. And now, using this, we can solve for KS. So how would we solve for KS? Well, first of all, you can cross multiply. So KS times 4 is 4KS. 12 multiplied by 3 is going to give you 36. And then if you divide both sides by 4 to get rid of the 4 on that side, then KS would be equal to, so 36 divided by 4, 36 cut into a half is about 18. 18 divided by 2 is 9. So KS is equal to 9 units. And there we go. So that's how we find that. Okay, so just take note of everything that they name and then see how it relates to the diagram. Remember, in all of maths, the previous question usually has a lot to do with the next question, especially in paper 2. Okay, moving on to the next question. So 11.2.4, the last question for Euclidean geometry in this paper, and really the last question for the paper, says, if it is given that NL is equal to 16 units and LS is equal to 13 units and KN is equal to 8 units, determine with reasons the length of LT. Okay, so since we have to find this, I'm going to keep this on the top. I'm going to keep it pinned to the top so I remember the lengths exactly they're speaking about. But it is also going to be helpful to write down the other lengths that we do have, like that KS is 9 units, for example. Okay, so let's go ahead and do that first. So I'm marking KS as 9 units. So keep that in mind that this is 9 units. And then let's see the other things that they told us. Okay, so first of all, I'm going to get rid of these angles for now. Hopefully we will not need them. Okay, because this is the last question anyways. So they told us first of all that NL is 16 units. So we have NL this being 16 units. So let's just see. 16. Okay, so we have LN as 16 units. Then LS is 13 units. So L to S. So this one, okay, this was not so bad. So this is 13 units. And then they also told us the length of KN. So KN is 8 units. Okay, that is interesting. So we already have 4K, right? We know that this is 4 parts, but now we know the length of it. It's equal to 8 units. This can help us to find K. And if we can find K here, we can also find out exactly what the length of MS is. Okay, so let's just focus on the whole goal. The goal is to find the length of LT. So to find LT, so how can we actually find LT? Let's just look at what exactly are they giving us, which triangle is it part of, and how can this help us to actually find this length? So notice that they want us to find LT, but they gave us the length of LN, right? If we just find this little part, we'll be able to find out exactly what LT is. Also, just notice that if we look at this big triangle, okay, this big triangle LNM, we have parallel lines here. Okay, so now this makes sense because look at the kind of things they've given us. They gave us the length of LS, which corresponds perfectly with LT. They also gave us the length of, well, they told us what MS was, that is 3 parts. And we know that we can find K because of this. So clearly we're using the proportionality theorem because we have parallel lines here. Okay, so this is the triangle we're using and we just need to find LT. Okay, so I just changed that highlight to a lighter color. So how we can find this is, first of all, we can say, because we want LT, we will take it as LT over, since they gave us the entire length of LN, we know that length now, we can use that as 16 units. So over LN, then it needs to correspond on the other side of the triangle, on this side as well. Since we took LT, we need to take LS. So LS over, and then because we took LN on the bottom, we need to take LM, okay, which we can actually find, LM. So now let's just focus on the things we need to find. As for LT, that's what we're looking for. That's fine. There's nothing we can do there. And LN, we already have that at 16 units. So we have LN. As for LS, on the other hand, we have that is 13 units. And then we need LM. So to find LM, if we can just find what this is, we'll be able to find what exactly the full length of LM is because we know what LS is. Okay, so we just need to find this. What is MS? Remember that here we already know that KN was equal to 4K, but they told us it's 8 units. So now we can find out exactly what K is. Okay, so we'll just say 4K is equal to 8. And then if you divide both sides by 4, K is equal to 2. Okay, so this is what I'm going to put down first. Okay, so moving back there, now that we found K, we can find the length of MS. By saying MS, we knew that was equal to 3K or 3 parts. And now we know exactly what that K is. So MS is equal to 3 times 2. And so MS is equal to 6. And that's why it's very important when they give you ratios, don't write it as numbers, because if you write it as numbers, you may confuse yourself and convince yourself that these were the lengths. They were not the lengths, they're just ratios. Okay, so call it 3K or 3A or 3B. Just put a letter so that you know it's not a length, it is a ratio. Okay, so I'll also include this calculation. Okay, so ms is equal to 6 units. And now that we have ms, we can find the full length. We know the full length of lm. Okay, which is really what we were looking for here. We had all of these ones. So that means that lm is going to be equal to the 13 units of ls plus the 6 units of ms, which is equal to 19 units. Okay, so I'll also include that. Okay, so there. And now we can go ahead and start working on finding LT. So we're going to use these proportions. We're saying the fact that LT over LM is equal to LS over LM because of the proportionality theorem. So I'm going to use that. And the reason I don't really say proportionality theorem is because there is a line drawn parallel to one side of a triangle. Okay, so it's really because of this. We have this triangle and we have this line being drawn parallel to one of the sides of the triangle. Okay, so now that we have that, we can just fill in everything that we have, okay, the lengths that we have. So now I'm just going to fill in the lengths that we have. LT is what we're looking for. We don't have that yet, but we know that LN, L all the way to N, is 16 units. So that's 16, I must put there. And then we have is equal to LS. LS is 13 units. And we know that LM, this full length together, because we found this to be 6 units. So it means that it's LM is 19. We already have that over 19. Okay, so this is what I'm going to put down. 16 here, 13 and 19. Okay, so we have the 16, 13 and 19. In order to solve for LT, we just multiply both sides by 16 to get rid of that denominator of 16. And so we're just going to have to say LT is equal to what is 13 over 19 times 16. And that gives us 208 over 19. And then we can leave it as decimals because in the instructions, it always says leave as rounded off to 2 decimal places. So that is 10.95 rounded off to 2 decimal places. And that is LT in units. Okay, so that is it for this paper and this Euclidean geometry section. I hope you guys enjoyed. Please do like if you enjoy the video. It really helps the algorithm. And I will see you guys in the future videos. Bye for now.